Welcome to the PLC Professor's Workshop. This video, and hopefully more to follow, is aimed at very basic learners. If you already have a firm understanding of electricity and magnetism, this video is probably not for you. Aiming it in particular with one young person in mind, Eduardo Guillaume, in the Dominican Republic. He's a Haitian who's in the Dominican Republic now, and he's a good friend. He's a young man. He's a good friend, and I'm endeavoring to introduce him to electricity, electronics, magnetism, and programming. So I'm starting with the very fundamental aspects of electricity. If you don't understand electricity, you might as well forget anything in the way of technology. The video you're going to watch is going to be made up of older clips, newer clips, where I've gone back and taken clips that I made specifically for technicians and electricians here in the United States that were learning industrial automation, and I explained electricity and magnetism. So I'm going to take pieces from those older videos and new pieces and blend them together. If you're a beginner, you will hear terms that you don't recognize. If your first language is not English, you will hear words that you may not know the definition for. That is your cue to pause the video, back up, listen to the word again, and check it out online to see what it means. And I will endeavor to keep this as simple as possible so that anyone watching that understands even just basic English can follow along and learn electricity, magnetism, eventually electronics, and programming. We're going to start at the atomic level and explain atoms. Atoms are so small, they've never been seen by the human eye. People might argue that you can see them with an electronic microscope. That's not true. You can sense them, but you can't see them. And everything on this earth is made up of atoms. And there are over 100 unique atoms in the list of elements, periodic table. Some of them are man-made, but let's just say there's about 70 or 80 elements like copper, iron, zinc, etc., that everything is made up of these atoms, and the atoms form molecules. So when we talk about atoms, remember that what we're showing you is a model of an atom that is a theory, but it's a theory that's never been disproven. And an atom is made up of a nucleus and then electrons that swarm around it, traveling at the speed of light. They travel so fast it looks like a cloud around the nucleus. And the electrons have a negative charge, and in the nucleus you have protons and neutrons. The protons have a positive charge. Each proton is equal to the charge of an electron, but opposite, so they attract. So you have this energy of the electrons trying to expand out from the core or the nucleus of the atom, but you have the positive and negative charges attracting to hold them in place, much like a satellite orbiting around the Earth. It wants to go out, but gravity's pulling it back. So let's jump in there, and remember, take your time. Don't try to skip over stuff. You could watch the videos all the way through, not trying to understand everything, but picking up what you can, and then go back and listen to them again. Because whatever you glean from the first view will be there when you go back to watch it again, and it gives you more focus on the things that you did not understand. If you are patient and you follow along, you will learn and you will be successful. I guarantee you, every person on the face of the earth can do this. Every human being can do this. So let's start right in. I want to add that there are introductions that were previously recorded to certain segments. I left those introductions in there, and it may sound like I'm jumping ahead. I'm not. I just left those in there because I want everyone to be able to learn from this. So I will be showing you some things that aren't relevant yet to you, if that's where you're at in your learning process. And if you are already there, so much the better. Today, I'm going to start a series that is the underpinnings for everything in industrial controls. And that is the things that support your understanding of the things that you see out there. This is the very basic stuff. The very first discussion we're going to do is on physics and chemistry, in a sense. And I would ask you, do you know what this is? Just at a glance. It has 3 leads on it: blue, brown, and black. It has a plastic face and it has a threaded barrel. Now, if you said that's a proximity switch or a proximity sensor, that would be recognizing what it physically is. But do you know what it does? More important, do you know how it does what it does? Now, this is probably a capacitive proximity switch. I can't tell by looking at the part number. I just grabbed it out of a box. But I see 3 leads here. I instinctively know that brown is positive, blue is negative, and black is signal or switching. So it has to have power, and then it also has to have the ability to flip the state of something. That would be the black wire. Now, the tendencies wanted to make black negative, but for standard sensors, and if I look right on the barrel, I can see some information here. I see it says it's a PNP, and I can see the colors and the designation for common, signal, and power. I mean, it shows this right on the barrel. But if you don't know what this is, that's a problem. If you don't know what it does, that's a problem. And if you don't know how it does it, that's a problem. Now, I don't expect you to know what this is just by looking at it. You're saying, well, that's not fair. I can't read what it says on it. Well, it's a transmitter, but I don't expect you to know what this is. If you already do know what it is, great. Transmitter. What's this? Everybody's going to say, well, that's a battery. Well, it's a dry cell. But if you said battery, that's cool. It's a AA. That's a particular size or volume or capacity for generating current at 1.5 volts. So you know what it is. Do you know what it does? Well, if you said it powers things, well, okay. How does it power things? What does it do? Push out electrons and suck in electrons? And how does it do it? These are all things that you need to know if you want to be highly successful in industrial automation. You know what this is? This is just a little cheapie I grabbed out of a drawer. There's 2 leads on it. Now, if you say, well, that's an electric motor, well, you're halfway there. The fact there's only 2 leads on it means it's probably a permanent magnet DC motor. Well, what does it do? Well, you put electricity on it, in it, through it, and it turns the shaft and it turns things. How does it do it? These are all the fundamental things. If you want to be an industrial controls engineer, and you're going to go out on the shop floor with your laptop knowing how to program a PLC, that's just a tiny piece of it. I can take an electrician who knows electricity really well, has worked on the shop floor. Oh yeah, that's a proximity switch, that's a limit switch, that's a power supply, and recognizes all these things, but really doesn't know much about what goes on in a PLC. And then you give me another person who knows how to program a PLC, but has not spent time out on the shop floor, doesn't understand electricity and magnetism real well. Between the two, I can turn the electrician into a competent PLC programmer, troubleshooter, faster than I can take somebody that's learned PLCs and turn them into a proficient programmer, troubleshooter on the shop floor. There's more to know about what's on the shop floor than there is to know about what's in a PLC. That's the reason for doing these discussions. So the first one we're going to do is basically physics and chemistry. We're not going to do any mathematical approaches. This is strictly a summary overview of the physics and chemistry behind electricity and magnetism. Let's do this. Welcome to the presentation on principles of magnetism and electricity. This presentation offers a very light introduction to the phenomena of magnetism and electricity. The important takeaway from this presentation is the general ideas and concepts. No math will be used in these slides, but we will highlight the relationships that are easily shown in simple ratio and proportions. The intent here is to give you a visual understanding of these phenomena. History has to give somebody credit for everything. So in this case, Thales, a famous Greek, some 2,500 years ago, noticed that after he rubbed a piece of amber with a woolen cloth, that the amber would attract lightweight items such as dust, straw, feathers, and lint. I'm guessing that he was probably polishing pieces of amber for the marketplace, and he was using a woolen cloth. This same principle can be discovered on a daily basis. I remember one time I was sitting in a restaurant, and when I eat by myself, I have nothing better to do than play with whatever's in front of me. I picked up the sleeve that my straw came in for my soft drink. I held one end in between my thumb and forefinger, and then I took my other thumb and forefinger and slid it along the length of the sleeve to flatten it out. I was going to fold it up or tie it in a knot, I can't remember now. But after sliding my fingers across that sleeve, when I brought my hand near it, it was attracted to my hand. That is static electricity. Our modern term, electron, is the Greek word for amber. So this is one of the many examples where the actual meaning of the word has no relationship to how it's used today. Quite a few years later, a cat named Dufay, actually in 1733, found that if he rubbed against a piece of glass, the glass and his fur would become charged or electrified. He also found that the charged glass would attract certain things that his fur would repel or push away. From this experiment, this cat decided that there were two elements of electricity and they were directly opposite. Although I'm sure that this is not the first instance of this discovery, it was almost 800 years later that it was discovered that the same phenomena was observed when other dissimilar objects were rubbed together. It was also noted that not all affected objects were attracted to each other. Some repelled away when brought near, and some were attracted when brought near. This is the origin of the concept of different types of static electricity. Personally, I never know whether or not to really believe this account or not. However, it's so widely accepted, it probably was true. But we've all heard the story in American history where Ben Franklin went out into a thunderstorm and flew a kite, and he had a string tied towards the bottom of the kite with a key hanging on it. And when lightning struck the kite, the key lit up. It glowed. This is not impossible. Nonetheless, we'll just take it at face value. Ben Franklin decided that the two elements of electricity should be named positive and negative. Now remember that he's supposing this from observable phenomena. He cannot actually see what's going on. So he surmised that there was something named positive and something named negative. Positive meaning an excess, negative meaning a deficiency. And these are the commonly referred to as plus and minus, or shown graphically as plus and minus symbols. And he surmised that there was a flow from an excess to a deficiency. And since positive is excess and negative is deficiency, he determined that this flow was from positive to negative. This was and is referred to as conventional current flow, from positive to negative. However, much later, when electron flow was discovered, it was discovered that the actual excess is an excess of electrons. And in the meantime, they had designated an electron as negative and an atom missing an electron as a positive ion. So the two were in conflict. So conventional current flow is called conventional because it goes back to Ben Franklin and electricity flowing from positive to negative.
whereas in reality, electron flow, the actual flow from excess to deficiency, is from minus to plus. And some schools teach conventional current flow from plus to minus. Other schools teach electron flow from negative to positive. It really doesn't matter because you can't see the actual movement anyway. So it's basically terminology to describe observed behavior, but not actually observed physical motion of something. I'm sure everyone listening to this presentation can provide multiple accounts of personal discovery of static electricity. Some of it benign, some of it humorous, and some of it maybe even painful. I remember I was walking through Disney World inside a building, and I noticed that there was a lot of static electricity. The atmosphere was just right, and dryness and what have you. And every time I got my finger near anything metallic, a big arc would jump off the end of my finger. So I was walking along with a friend and his brother, and I scuffed my feet really good, got a good charge going. I reached around behind my friend and put my finger up behind his brother's ear, just close enough to get a big arc. It sounded like snap, like breaking plastic. And boy, did he jump. Now, you probably think that's mean, but anyway, not bad as Reuben here, because eventually that static charge is going to dissipate and down those babies are going to come. This list is called the triboelectric series. If you read down through this list, human hands, usually too moist though, are very positive, down towards the middle, steel, which is neutral, and down towards the bottom, Teflon, which is very negative. Through the years of experimentation, this list was put together and the order verified. So some objects, when rubbed together, display a very strong force while others are very weak. As objects of different composition were experimented with, this list evolved. Today this list is as you see it here on the screen. The materials at the top in red text have been determined to give up electrons to the materials lower in the list. Yes, that means that when you rub glass and fur together, you get static charge even though they are both in the upper half of the list. Another example would be silk and cotton. They're both in the upper half of the list. If you rub silk and cotton together, and ladies have probably discovered this more than men, wearing a cotton undergarment and then a silk blouse, but this combination is available for the guys too. And maybe you were undressing in the dark, and as you were pulling off your silk blouse, you felt some static discharges and maybe even saw the sparks. Many of us have been known to do this in the dark just to see the sparks. Now, if you take silk and rub it against glass, the silk is now negative compared to the glass. So it's the relationship of plus to minus is determined by where they're at on this list. The higher on the list, the more positive. The lower on the list, less positive. In the first case of silk and cotton, cotton rubbed against the silk stripped electrons off of the silk, leaving some of the atoms in the silk missing electrons and therefore positive. Whereas when silk is rubbed against glass, the silk actually rubs electrons off of the glass, and the silk is now negatively charged with an excess of electrons, leaving the glass missing some of the electrons from the outer orbits of its atoms. So it is proper to say that the silk is more positive than the cotton, and yet less positive than the glass. So the most positive is positive, and the least positive is therefore negative. The same rules apply throughout the list, top to bottom. So at this point, you should be realizing that electricity is the separation of charges. An atom, electrically neutral, has an equal number of positive elements and negative elements. But if you remove one of the negative elements, then you have more positive elements than negative elements left behind. Therefore, you have a net balance of positive. And whatever device took the electron away, it now has an extra electron, therefore it's negative. Producing an electrical charge by creating friction between two dissimilar materials off of this list was the first method discovered to produce electricity, and everything else followed as people became more familiar with the phenomena. Now remember, this was discovered, we'll say, by Thales, the ancient Greek, and then he showed it to friends. Eventually this gets around, people play with it and they experiment, and then they draw conclusions. A lot of what is known about modern electricity is still based on those basic conclusions. This older gentleman here, Dmitri Ivanovich Mendeleev, is basically credited for the periodic table. And we give a date here of 1869. This is just to give you a chronological reference.
This is where we're going to end the first video. I've actually interrupted a longer video about 1/3 of the way through to try to alleviate extreme boredom and becoming fatigued from watching stuff that's new to you. But hang in there. So in the next video, I'm going to jump to a completely different area, and I'm going to do something that's more practical looking, something that you will enjoy. Then we'll come back to the technical stuff. See you in the next video.